All right, in this tutorial, we're going to go over in the Algebra 2 section of the Big Ideas book, 2.2, Characteristics of Quadratic Functions. So we're going to talk about some different properties that you're going to see in parabolic functions, finding maximum and minimum values of the quadratic functions, and that's going to depend whether it's opening up or down. Graphing quadratic functions using x-intercepts, so where it crosses the x-axis, and then being able to solve real-life problems. So we're going to jump straight into the first example and graph this quadratic equation, and then label some important parts of this function. So first thing is to graph your negative 2x plus 3 squared plus 4. Your constants of a, h, and k. If you don't remember what those are, we talked about h and k in the last example of your vertex, and then your a is the stretch and reflect property. So plotting that vertex of negative 3, 4, because you know that that's right in the middle, and then drawing your axis of symmetry at negative 3, because that's where your vertex is. Evaluate your function for just a couple of those random points of two values in the x-coordinate. So just pick easy ones like the first point to the right and the first point to the left after that. So we're going to choose negative 2 and negative 1 in this example, plugging them into the x value of your quadratic function and simplifying down to get your y values. So you have a coordinate point of negative 2, positive 2, and negative 1, negative 4 after you've evaluated them. So plot those points. And then you're going to reflect them over to the other side of your axis of symmetry, because remember, quadratics have axis of symmetries going through them vertically. And then connect the dots in a curve through those plotted points. All right, so another form of quadratic functions that we can go over is standard form. Standard form you're going to see is written as ax squared plus bx plus c, where a, b, and c are numbers. They could be whole numbers, they could be fractions. But as long as a exists. So if your a is 0, then it's no longer a quadratic function. So your a could be 1, it could be anything that's, as long as it's not 0. So when your a is positive, like this first example right here, your a is greater than 0, that means your parabola opens up and your vertex is a minimum value because it's the lowest that it could be. Now, a formula that you're going to be using frequently in order to find axis of symmetry is taking the opposite of your b and dividing it by 2 times a. So that's what this negative b over 2a right here is. And it's always going to be an equation. It's always going to be x equals a number. It could be a fraction decimal, but it's x equals a number as an equation. That's going to be your axis of symmetry. Your y-intercept is always going to be the coordinate point 0, c. So whatever number is in your c position, that is going to be your y-intercept. Then to evaluate the y-coordinate of your vertex, your x-coordinate is always the same as your axis. Your y-coordinate is just when you plug that into your equation and then evaluate, you get the y-coordinate of your axis. So let's start with our first equation, finding the vertex and the axis of symmetry. So right now, this quadratic is written in standard form of 3x squared minus 6x plus 1. Your a is 3, your b is negative 6, and your c is 1. Those are your 3 important constants that we're going to talk about. Because your a is positive, it's important to know that your parabola opens up, which means that your vertex is a minimum value. So let's go ahead and find the vertex. But first, we need to be able to find the x-coordinate or the axis of symmetry. So we're going to use our negative b over 2a. So because your b is already a negative 6, the negative 6 is up here, but that negative out in front is always going to happen in this equation. Then on the bottom, 2 times a, which is 2 times 3. You simplify that down and you get positive 1. So your axis of symmetry is the equation x equals 1. When you have x equals 1, you then plug it back into your original equation. Instead of x, you plug in 1. Simplify that down, and in this problem we get -2, so that means this is the y-coordinate of your vertex. Your vertex is a point, so you have to have an x and a y, so the vertex is the coordinate point 1, -2, and that's the first point you should plot. Draw your axis of symmetry, which is going to be a vertical line through that vertex. And then again, identifying our y-intercept, which is the coordinate point 0, c, and in this example, the c is +1. Plot that point reflected over the axis of symmetry. And then you can just pick another value of x so that you know whether it's being stretched or compressed or something like that. So in this example, the next easiest one after 2 is a +3. Or if you wanted to go to -1 over on the left-hand side, either one works. So for this one, we evaluated at 3, 10 as a coordinate point, and then you reflect that over to -1. That way you know how far up and over it's going to the next point, because this is a parabola. It's going to curve. Connect the dots, draw the lines, and there is your quadratic function. So because the vertex is always either the highest or the lowest point, depending on whether it opens up or down, the y-coordinate of your vertex is always going to be considered the maximum or the minimum value. So because it curves, it can either peak at the highest level and then come down, or it can curve down and meet the valley and then come back up. The vertex is always on the axis of symmetry, so the function is either increasing or decreasing depending on which side of that vertex you are looking at. So if your a is positive, which means it opens up, it's decreasing on the left side and then increasing on the right. Or if you flip it, like this one, your a is a negative number, it's increasing on the left and then decreasing on the right. So if your parabola is pointing up, your vertex is a minimum. Your domain is going to be all real numbers because the graph can go forever to infinity on the left, forever to infinity on the right. And then your range is all values above your minimum value. Okay? Same thing over here if we flip it. Because this parabola is pointing down, your vertex is a maximum value. Domain is still all real numbers because it goes forever to infinity left and right. And your range is all y values less than your maximum, because maximum means highest. So let's go ahead and find the minimum or maximum value of this parabola, 1/2 x squared minus 2x minus 1. Talk about its domain, range, and then where it's increasing or decreasing. So first we need to identify our a, b, and c. So our a is 1/2, b is -2, c is -1. Because that a is positive, the parabola opens up, which means that the function of the vertex has a minimum value. It's the lowest. So we need to find that minimum value by finding first the axis of symmetry. So we're using the formula -b/2 times a, plugging in -2 and 1/2. Simplify that down, you get x equals +2 as the axis. Then take that 2 and plug it into the x value of your equation. 1/2 2 squared minus 2 times 2 minus 1 gives you -3. So your vertex is the coordinate point 2, -3. And we already talked about, since the parabola opens up, that the minimum value is -3. So the range is all values above 3. Domain is always going to be all real numbers. That will never change as long as we're talking about parabolas. The function is decreasing to the left of x equals 2 and increasing to the right of x equals 2. Remember, we're just using that same x equals 2 from our axis of symmetry. So you can always check it by plugging it into a graphing calculator or using that website Desmos, and you can find that minimum value to -3. All right, so intercept form is another thing that we're going to look at for quadratics. So we've talked about vertex form, which is the h and the k. We've talked about standard form, which is your ABC. Intercept form is going to help you easily identify the x-intercepts. So it's written in the form of a times parentheses x minus p, parentheses x minus q. So this is, if you think about it in factored form, when we continue on and talk about quadratic equations a little bit more. So because that your two values, when they get multiplied together, could possibly equal 0, you're going to have possibly two different values where the parabola could cross the x-intercept. So you could have one that's to the left of your axis of symmetry for your P. You could have one to the right of your axis of symmetry, which could be Q. In intercept form, your axis of symmetry is just taking P plus Q and cutting them in half, which is another way to say you find the average of the intercepts, because the axis is the halfway point between those two. Your A value still does the exact same characteristics. If it's positive, it opens up. If it's negative, it opens down. So let's look at a quadratic in intercept form, graph it, label the x-intercepts, the vertex, the axis of symmetry, all that. So this is still a quadratic function. It may look different than the ones that we've done like in the standard form. It may not have the exponent of 2, but if you think about it in factored form, a quadratic could look like this, but it makes x-intercepts much easier. So the x-intercepts, we're going to look at the numbers that are inside our parentheses and then take the opposite signs, because the formula is x minus p and x minus q. So that means that since it's x plus 3, we are taking minus 3. And since it's x minus 1, we're taking positive 1. So those are the 2 points where the graph crosses the x-axis. Then we're going to find the coordinates of the vertex, which means we're going to take the average of our p and q to find the x value, or the axis of symmetry. So -3 plus 1 divided by 2 is -1. Then evaluate in our original quadratic, plugging in -1 to get 8. So your vertex is the coordinate point -1, 8. Which makes sense because the vertex is above your x-intercepts. Our A is a -2, which means the graph should be pointing down. So that vertex is a maximum value starting at the top of 8 and then going down to both the left and the right-hand side. So then you draw your parabola through that vertex of points where the x-intercepts are going to occur. So you can always check that by in a table. Also, Desmos has a little table chart function that you can use to look at some different various points between all of your x values. It'll evaluate for y. So there's your x-intercepts. You see where the y values are showing as 0, where y is equal to 0. It's your x-intercept, and then your vertex is the highest value in this example because the graph is pointing down. So one last real-life problem. Parabola shows the path of your first golf shot, where x is the horizontal distance and y is the height in yards. Path of your shot can be modeled with that following function of -0.02x times x minus 80. Which shot travels further before hitting the ground and which travels higher. So first you're given a graph and a function that represents the path of 2 different golf shots. So the graph is your first one, the function is the second one, and you just need to ask which one goes further, which one goes higher. So we need to determine first which one has the furthest x-intercept to the right, and which one has the highest maximum value of each function. Compare those 2 values and see which one is the most. So first, we're given in the graph that the maximum value is 25 on that vertex, and the x-intercept of 100 means that it traveled 100 yards away from him, but 25 yards in the air. So that's just interpreting the graph of the picture that's given. Next step, we need to identify the values of the equation of the first one. So because your axis of symmetry that is halfway between, your maximum height is 25 by taking 0 plus 100 and then cutting that in half. So that's where you get that 25 from. It's also labeled right there on the graph. So looking at the function, so rewriting that in intercept form, you can essentially say the obvious that x minus 0 is what's happening at that first -0.2 times x, because subtracting 0 doesn't change any of that values. And that kind of tells you that the ball is starting at an X distance of 0. You're hitting it 0 yards away from where you're hitting it, if that makes any sense. But then your other one, minus 80, tells you that the furthest x-intercept is 80, which you can already see is different than the 100, so we can compare that later. But the maximum height is if you find the average between 0 and 80, divide by 2, you get 40 for your x value, and then we have to plug that back into the graph of all of our x values. So multiply by 40, take 40 minus 80, and you get 32 for the height of the second shot in that function. So because 100 yards in that first graph picture was further than 80, your first shot travels further, but the second shot has a maximum value of 32, which is more than the maximum value of the picture 25. So the second shot traveled higher. So you can look back and check that in the graphing calculator, that second shot goes higher than 25, which is what that first picture was. And yes, that it's continuing up further along, even all the way up to 32.